In today's lesson, we're going to continue working with triangle congruence, but we're going to learn some shortcuts in how we can prove triangles congruent. So we're going to apply SSS and SAS to construct triangles and solve problems, and we're going to prove triangles congruent by using SSS and SAS. So we'll learn what those acronyms stand for. But some new vocab, triangle rigidity, we won't really use that much, but we will mention it, and we will need to know what an included angle is. So, if you remember in lesson 3, we proved triangles congruent by proving all the pieces of the triangles congruent to each other. So all three sides congruent to the other three sides, and all three angles congruent to other three angles. Well, the property of triangle rigidity gives you a shortcut for proving two triangles congruent. It states that if the side lengths of a triangle are given, then the triangle can have only one shape. So let's say we have a triangle with side lengths 3, 4, and 5. No matter how we move 3, 4, and 5 around, it will always create the same triangle. The angles can't change. So, for example, you need to know that two triangles have three pairs of congruent corresponding sides. This can be expressed as the following postulate. So we will always use the acronym, but we need to know what that stands for. So the side congruence postulate says if three sides of one triangle are congruent to three sides of another, then the triangles are congruent. So if you can prove three sides congruent to three sides, you know that the triangles are congruent because of SSS, and you don't have to mess with the angles. Now remember that if we have adjacent triangles or triangles that are right next to each other sharing a side, you can apply a reflexive property to give another pair of side lengths congruent. So for example, let's look at this. It says use SSS to explain why triangle ABC is congruent to triangle DBC. So in the picture you can see they tell us, notice the markings, we need to know what those mean. They tell us that side AC with two dashes is congruent to side DC with two dashes. They also tell us that side AB is congruent to side DB by showing us with the marks. So those are given to us. And the third side that we need to prove, notice, is a shared side from both triangles. So BC is a part of this left triangle. BC is also a part of the right triangle. Well, BC is the same line, so we know that that segment is congruent to itself because of the reflexive property. So now we can say that the triangles are congruent to each other by SSS. Let's look at one more. Use SSS again to explain why ABC is congruent to CDA. Well, notice once again in the picture it gives us two sets of sides congruent, AB and CD, as well as BC and DA. So those are congruent because it shows us in the picture. Now the third side of the triangles is a shared side, and we know that AC from this triangle is congruent to AC from this triangle because it's the same line, so reflexive property. Now we have three sides congruent to three sides, so the triangles are congruent by side, side, side. Now our other vocab word we needed to learn was the included angle. So if you think about being included in something, you're kind of in the middle of it. You're a part of it. So an included angle is an angle formed by two adjacent sides of a polygon. So B is the included angle of sides AB and BC. So included means it's between them. So if I was using AB and BC, notice C is not a part of AB, so that's not included, it's not in the middle of them. So we will use the included angle when we use our next postulate. So it can also be shown that only two pairs of congruent corresponding sides are needed to prove the congruence of two triangles if the included angles are also congruent. So say you can't prove all three sides congruent to each other, but you can show that two sets of sides are congruent as well as the angle in between them. Now you have another postulate you can use, the SAS or side angle side postulate, that says if two sides and an included angle of one triangle are congruent to two sides and an included angle of another, then we can prove that the triangles are congruent. But notice with the SAS or side angle side, the letters are important, they do matter. A is always written in the middle, because the congruent angles must be between the pairs of congruent corresponding sides. So A must be between the two sides. So let's try and put that into action. It says the diagram shows part of the support structure for a tower. Use SAS to explain why the top triangle XYZ is congruent to the bottom triangle VWZ. So notice in the picture with the markings, we are given that two sets of sides are congruent. The one dashes, the XZ and the VZ, are congruent to each other. And the double dashed lines, YZ and WZ, are congruent because that's given. Now we need to figure out their included angle. Notice that's going to be the angles that are in between those two sides. Well, remember, anytime you see lines cross, we're looking for vertical angles, and those two included angles are vertical angles in that picture. So we can say that the included angles XZW or XZY and VZW are congruent because they're vertical. So the triangles are congruent because we have side angle side congruent to side angle side. We'll try another one. Kind of putting a couple ideas together. We're looking for why SAS is going to help us prove our two triangles congruent. So remember, always look at what we're given. We have one set of sides congruent. It also gives us a set of angles. ABC and DBC are congruent. So we've got a side and angle. Notice that means for SAS we need another side. So we want the angle to be included, and we see that BC is a part of both triangles. Anytime you see two triangles that are sharing a side, you're probably going to use reflexive property. So BC from the top triangle is congruent to BC from the bottom triangle because it's the same segment. So reflexive property says it's congruent. And once again, we have side angle side congruent to side angle side. So we know that the triangles are congruent. The SAS postulate guarantees that if you're given the lengths of two sides and the measure of the included angle, you can construct one and only one triangle. So kind of like earlier, if you have all the sides congruent, you can only construct one possible triangle. Well, if you have two sides and the included angle, there's only one possible triangle that can be created. Alright, let's look at just a few more examples. First of all, show that the triangles are congruent for the given value of the variable. So we did this last unit with our angles and our parallel lines cut by a transversal, so it's the same idea. Notice if they already gave me x, I'm not solving for anything, but we want to see if the triangles are going to have the same side lengths if when x is 5. So the first thing we're going to have to do to find these side lengths is plug in 5 for all of our segments. So if we start at PQ, where we have x plus 2. If I plug in 5 for x, 5 plus 2 is 7. So notice in our congruent statement, remember where the letters are means something. So notice PQ were the first two letters of this triangle. We want them to match the first two letters MN. MN is 7, and we said PQ is 7. So far we're good. The same so far. Well, QR is just x, so we know that this segment QR is 5. QR is second and third, so we want it to be congruent to NO, which is also 5. So that checks out. Now we'll look at PR, which is 3x minus 9. So we'll replace the x with a 5. 3 times 5 is 15. Minus 9 is 6. So 6 PR first and last. MO is also 6. That means yes, our triangles are congruent because we have all sets of sides congruent. So I can use SSS. Alright, we're going to look at two more proofs. We're going to fill in the blanks. This says given BC, that's supposed to be parallel to AD, and BC is congruent to AD. So those two segments are parallel and congruent, and we want to prove our two triangles congruent. So first of all, how did we know that BC was parallel to AD? Remember, we always start with the given. So that was given to us. I see it up here, or what it's supposed to be. Now we're filling in the reason for alternate interior angles theorem. So remember, that's from last unit when we have a transversal. So if we look at our parallel lines, to find angles that are in both triangles using a transversal, I'm going to assume we're using BD as a transversal. So the two angles that are alternate and inside using BD, I have CBD, this angle right here, should be congruent to this vertical, or this alternate interior angle, ADB. So we had given, and we had a CBD congruent to ADB. Now we have a side and an angle congruent to a side and an angle. Now we have another piece of given. We remember that the only other piece that wasn't given was BC and AD. So we're going to plug that in as our other given. Now why would BD be congruent to BD? Now notice we're saying two pieces are congruent to themselves, so we're using the reflexive property. And notice in our picture we have a side, an angle, and a side congruent to a side, angle, and a side. So we're using side, angle, side to prove those triangles congruent. Okay, we're going to look at one more quick example. In this one it says we're given that QP bisects RQS, so we're going to need to know what bisects means. And in the picture you can see the markings. QR is congruent to QS. So we're going to try and prove those two triangles congruent. So notice we know that QR is congruent to QS because it's given to us. Now how do we know that QP bisects RQS? We'll look at that, it matches, it's given. Now using definition of bisect, well, if we know what bisect means, it means to cut in half. So we know that the halves are congruent. So if QP is bisecting RQS, the two halves would be RQP and SQP. So using definition of bisect, that's what we have there. Now using reflexive property, the pieces that are shared in both triangles are segments QP. So QP is congruent to QP. That's showing our second set of sides congruent. So notice we said side, angle, side, congruent to side, angle, side. So using our reason, remember we're proving those two triangles are congruent, so that's our last statement. Alright, we'll practice these in class. I'll see you soon.